today, Chris Keane. Chris has been the WSU Vice President for Research for about the past 10 years, and he's currently on research leave in the calendar year. He has had numerous leadership positions in the past, not only at WSU, but also at LNNL. For example, he led the NIF user office from 2009 to 2014, and he has been on the DOE National Nuclear Security Administration. And in this capacity, he managed the inertial confinement fusion program from 1997 to 2007. And this had an annual budget of 700 million per year. And his technical work includes computational and experimental studies at Lawrence Livermore, in the direction of inertial fusion and X-ray lasers. And he's very excited to join the physics department formally in January. There will also be a lot of student opportunities. And so for the students, I think he will also tell a little bit about student opportunities in his talk today. So Chris holds a BS degree in physics and engineering from the University of Rochester and a PhD in astrophysics from Princeton. And he's a fellow of the American Association for the Advancement of Science. He's a member of the Washington State Academy of Sciences, and he's a member of the American Physical Society. He is the recipient of an NNSA Silver Medal, the Defense Program Award of Excellence, and the Fusion Power Associates Special Award. So we're especially happy to have you here, and please, welcome to Keane.
Thank you, Peter, for that. Okay, good afternoon. It's great to see you all. So I'm excited to tell you a little bit about high energy density physics today, and I will highlight some of the opportunities for the students in this really fast and emerging field. So it's really an exciting time. I hope I can convince you. So like I said, I'll give a quick overview of the field here, high energy density science research, and then of course I'll talk about the recent achievement of ignition at the National Ignition Facility, which is really a Wright brothers moment for fusion, right? We know that ignitional fusion will work. Okay, and it can produce net energy. The only question is how much will it cost? Important question. Okay, and can we do the technology to make it actually come fast? And then I'll talk a bit about fusion commercialization, actually, which is something I'm very involved in right now because, in fact, there's been some alumni from our department that now work at the companies in the Northwest. We're a hotbed of fusion commercialization activity here. We'll talk about that. Okay, so let me start with high energy density science. So here on the left, I've got a little phase diagram of it. And you'll note that, and this is a definition from the National Academies who've done many field surveys of this field over the last 10 or 20 years and pointed out the important emerging opportunities, which have been largely driven, by the way, by facilities that used to be focused at the National Security Laboratories and national security only. Now they're focused on science, and so all of a sudden these tremendous capabilities to make high pressure are available to academic and other researchers. Anyway, so 1 megabar is sort of the National Academy defined limit. I'll talk more about that in a second. Just as a quick comparison, from your classes, you remember the Rydberg, the ionization potential of the hydrogen atom, 13.6 eV into the Bohr radius cube. That's sort of the atomic unit of pressure. That's about 30 terapascals, which you can see in the chart there. It's a little over a megabar, it's a few megabars. So above that energy density, the energy density in the system actually approaches or is greater than the energy density associated with the atomic level. So if you do things like spectroscopy of high energy density systems, everything is completely messed up, right? Lines are stark broadened, lines are shifted, but that's what I did. I did X-ray spectroscopy. And of course, there's also radiation transport and all kinds of astrophysical phenomena going on too. So it's really an interesting thing. Anyway, greater than 1 megabar is the border there on the left again. Center of the Earth is about 4 megabars. The center of Jupiter, about 50 megabars. The center of the sun, 2 to 500 gigabars, approaching a terabar. Okay, and up there on the left side, you can see, hot matter, low density. That's a plasma, right? That's sort of the normal area of matter that we're used to there on the left-hand side of the plot. So that's an overview. And by the way, if you're interested more in this field, the Academy's report is on the web. It's free. All you have to do is sign up and tell them what you're going to do with it, and they'll go through a lot more opportunities. So anyway, so these science capabilities that I've talked about really support 3 major missions for the DOE. One is national security. which is basically happens at our national security lab. So high energy density science is basic physics. That's what it does. That's important. Just understanding that science. So that's the technical connection, but also bringing in people, right? That's vitally important for any program. So really, it's all about the people and fundamental science for national security. Over in the fundamental HED science itself, a lot of materials science. This is kind of a cool picture that I won't get to discuss much more about. That's the Eagle Nebula. Those fingers are actually fingers going from the Rayleigh-Taylor instability, hydro instability. I'll talk about it in for ICF targets. And that's about 10 light years along the vertically, right? So that's a lot of instability growth, 10 light years growth. So that's just one of some of the physics that's being done. And then, of course, fusion energy, which uses for most cases DT as a source. Deuterium comes from seawater. Tritium, of course, has to be made, and I'll talk about how that's done in a fusion reactor in a little bit. Okay, I just want to mention too that advanced computing is crucial for high energy density physics and really all missions, but it's because high energy density includes a lot of different phenomena: fundamental materials science, radiation transfer, atomic physics, and in the presence of high fields. Right, so very complicated atomic physics. So a lot of basic areas of physics are very involved in this subfield of research. This is a picture here of El Capitan at Livermore, which is the next big computer coming their way, which is vital for all the simulations I'm going to show you for ignition and science and all the other national security missions. But this is going to be an exascale machine, 10 to the 18th flops. Okay, and I think many of you who are computational scientists know that it's one thing that it's hard enough to build such a machine. It's actually even harder to figure out how to use it intelligently, right? Because it's the old days of easily paralyzing things are behind us, right? It's really tricky to use a machine like this effectively, but it'll be really exciting to get it on board and working. So let me just say a word about HED science experiments and how to think about them. So, obviously you're making materials at high pressure, right? So you're going to need to apply a lot of energy to a system to do that, okay? And the exciting thing is that, you don't have to do it at a NIF, right? There's NIF in the middle. It's obviously big, very big, right? But you can actually get high energy density conditions. On the left, this thing called ELI, which stands for Extreme Light Infrastructure in Romania. And it's a long story. The lasers at ELI are actually built by a US company. That's another story. Okay. But the interesting thing is that ELI allows you to get very high energy densities in a small amount of matter by going with super high power, right? So with ELI, you can get 10 to the 16 watts, which actually is higher power than NIF, but you get it 1 kilojoule of energy in a 1 micron laser spot. So you make a micron scale high energy density plasma there. NIF can deliver 10 to the 15 watts, but into a 1 millimeter area with a megajoule of energy. So if you have a macroscopic target like a fusion target, NIF is your choice. If you just want to do basic science, you can do it at the university lab level with very high peak power lasers. It's very exciting. And in fact, that has driven development of a whole network of laser user facilities around the country over the last 10 to 15 years. This has been propelled by National Academy of Sciences reports that have said it's really important to democratize these high power lasers and get them out there. So most of these laser facilities that are shown here are operated short pulse, right? They can get high power, they can make high energy density plasmas and some, but a small volume. At the University of Rochester, some of you may know, the Omega laser there is a big fusion laser. It's actually also open to academic researchers from all over the world. They have a program there which allows you to propose experiments. You can even get paid to do them. So I think that's a great way for students at WSU to get involved in the areas, to apply for shot time on these lasers. If you get shot time, it's typically a week. You get a week, okay, and you can do, Dan and Jim know this, 15 or 20 shots or something like that. On Omega. Okay. So you can do pretty much a full experimental campaign in a week if you plan it right. You've also noticed that I put Institute for Shock Physics up there on the upper corner of the map. It's not a laser, but it's the same idea, right? I mean, for those of you who haven't seen it, Jim or Dan Dolan can take you on a tour. But it's very accessible to students. It's student scale, right? And that's really an important feature. This field, and you can see in the parameter space on the right, you can see and it's plot pulse width versus pulse duration. And generally, it's mostly short pulse. The little inset there shows some user facilities that operate at long pulse. It's Slack, Livermore, and also Rochester. So user facilities are out there. So, what's some of the exciting science that's been done? Well, a lot of it is material science because we have no clue really until we got these facilities what happens at 500 megabars of pressure in carbon or something like that, right? So one which I think is really fun is on the upper left, which people have done a lot of work on carbon because it's ubiquitous, obviously, in the universe. But so the latest thinking on Uranus and Neptune is that conditions present on the planet, 50 million atmospheres, 50,000 degrees, you're sort of near an equilibrium point for diamond, high density carbon, and there could be oceans of diamond with icebergs and diamond rain. You can imagine that. I mean, it's just a total mind blower, I think, to think of that. But it'd be fun to go visit it and see how it feels like. Another thing there's been a lot of work to create and characterize metallic hydrogen. Okay, this has been a goal of physicists for a long time. The advent of high pressure facilities has enabled it to happen, right? And that's enabled us to better understand planetary interiors. And so one of the things that's happened in this whole study of constitutive properties of materials or planetary interiors is that we now can understand what's going on with exoplanets, of which there's now slightly over 5,000, much better. So if you do exoplanet science, what you typically get out of an observation is the mass and the radius or a mass radius relation, right? But if you know the constitutive properties by doing a fundamental experiment of EOS at 50 megabars, you can tell whether that exoplanet you discovered is rocky or a gas giant, maybe, right? So you can tell whether it's capable of supporting life someday. So it's really interesting connection there. Then, of course, the ignition is another big breakthrough. There's also a number of other things having to do with the opacity, radiation physics and stellar interiors, opacity, things very complicated. So there's tons of stuff you can do with stellar interiors as well, which I can't get into here today. But it's a lot of it's in that National Academy. And there's great science coming out of HED science, but I also want to point out some important spin-offs. So this is a picture of an extreme ultraviolet lithography machine. It's built by ASML, that company in the upper left, which is a Dutch company. And some of you may have heard about it because this is the machine that enables TSMC, Taiwan Semiconductor Manufacturing Corporation, to build the world's supply of Apple chips, which are typically made right now at micron scale features, right? Which is why your iPhone, see at the bottom there, about 20 million transistors, right? So the way that ASML machine works is that basically there's a pattern, it's irradiated by X-rays, the pattern is made down on the resistor, etch off the remainder of the resistor, and you've got your circuit with micron scale features. Well, it turns out that all the technology to develop the X-ray source for that and the illumination techniques was done as part of fusion X-ray diagnostics. Guess what? You have to take really high resolution X-ray pictures of high energy density plasmas. And so I wish in the US we managed to keep this thing here rather than have ASML do it. But this is actually a spin-off of high energy density physics, the $500 billion per year chip industry. So great example of what happens when you do good science. You don't know where it's going to go. Okay, so now that's a spin-off of fusion. Let's now talk about fusion itself. So first of all, fusion, I think as we all know, but it's really everywhere around us, right? It drives our sun, but the fusion reaction in the sun was, discovered by Eddington and others around the beginning of the 20th century. It's different than what we use in power plants. It's basically straight hydrogen fusing. It's a very complicated chain. You wind up with helium, but it's very slow. I mean, it turns out the average fusion reaction, the average time for a fusion reaction, if you're a proton in the sun, is 10 to the 9th years, which is why the sun is 10 to the 10th years or plus old, right? So it's kind of nice for us that it's very slow. Okay. That's not good for practical fusion energy. So we use a different reaction. I'll come to that. Now, of course, the other place that fusion's around us is in supernovas and the formation of the elements. I think maybe the best way to show this would be a periodic table with every element, lithium and above blackened, right? Because they all come from novas or supernovas, right? But when you talk about fusion with the general public, people don't even know that, right? But in any event, and some of the phenomena here is just fascinating. As many of you know, you start out in these high mass stars fusing hydrogen to helium. That helium fuses to carbon. You eventually wind up with iron core, which emits no energy to support the rest of the star. Eventually it collapses, explodes. It's just unbelievable stuff, right? But in any event, fusion is all around us. Okay. So how do we make practical use of it on Earth for energy? Well, here's how. So the fusion reaction, the preferred fusion reaction for energy production is DT. The cross section for that is, I think it's at least 15 orders of magnitude greater than the cross section for PP fusion in the sun. Okay, which is good because we don't want to wait 10 to the 9th years for one cycle of the fusion reactor. But the main fuel that's considered is DT right there in the middle panel produces a neutron and an alpha particle. Of course, the mass of the resulting neutron and alpha is less than the mass of the original constituents. And that delta E equals MC squared goes into the kinetic energy of the two products, right? And so the way that works is that, and I'll show more about this later when it's in the reactor, the helium that comes out of the fusion reaction is the alpha particles typically trapped in the surrounding fusion fuel and heats it, okay? So the idea is that you get a little core of DT fuel burning, as I'll show you in a little bit. And then the alphas are trapped, they heat it, and then it makes more fusions, more alphas trapped, that heats that, and then you wind up with sort of a runaway reaction and everything fuses and you get a lot of energy. The neutron, of course, comes out, right? And in most fusion reactors, it's used for two things. One, it's used to breed tritium. Neutron plus lithium-6 breeds tritium. And since tritium has half-life of 11 years, if you're a fusion reactor, you have to have a constant supply of tritium made for you. And then the other thing is that the neutron, you can actually put lead or other high Z materials in there, and you can basically have neutron capture and other neutron phenomena to heat the blanket. And so that heat is extracted, and that's what's used to produce electricity. So the neutron ultimately makes electricity and breeds tritium. The alpha heats the rest of the fusion fuel. And you all know about fission. It's heavier materials, so it's very different. There's no heavy high Z elements in a fusion reaction chain. The main thing you have to worry about is the neutrons activate the facility. They activate the stainless steel vacuum chamber, so you have to worry about activation, which is why some people study alternative fuels, right? So these are the main fuels looked at for fusion. DT on top, you can see it's got the highest cross section, and the cross section is also at lower temperature, so it's really much easier to achieve high fusion gain with DT. But the other fuels are attractive because they don't have a neutron, right? So that one of the private companies in Washington State, Zap Energy, is looking at DT, but there's a company called Avalanche over in Everett, which is looking at proton-boron 11 fusion. It makes 3 alpha particles and no neutrons. And then Helion, some of you may have heard of, they have over $1 billion invested. It's using D-helium-3, which is really challenging because it requires very high temperatures, 200 kilo electron volts. That turns out to be very, very high. Most of these HED facilities are 100 kilo electron volts in temperature or less, but that's a variety of the fuels, but we'll just consider DT for the rest of today. Okay, just a little more on energetics. So fossil fuels, your sort of your standard size 500 megawatt or 1 gigawatt coal plant requires about 10,000 rail cars per year of coal, right? That's an awful lot of dirty coal. It's CO2, the burnt combustion, which will go into the atmosphere, right? Well, why is that? Because it's chemical combustion. So the energy per gram is not great. It's 10 to the 4th joules per gram, pretty typical for chemical potential energy. Fusion is, of course, nuclear. So it's of order of 10 to the 11th joules per gram, which is great. And so, if you have 3 sort of, water cooler sized jugs of DT, not just water, it's got to be DT. Okay. A lot of people just put 3 water coolers up and say, if you don't have 3, a little bit of water, it's got to be DT. Okay. But in any event, you can obviously see it's a big win in terms of the fuel, and the radioactive waste stream is much less because it also really the only thing is activation. You don't have to do any spent fuel storage. Okay, so you want to use DT, you understand why fusion is attractive. So what are the ways to do it? Okay, there are basically three major concepts that have been looked at. The first one I'll talk about is the NIF, which is over there on the right. That's the laser fusion. I'll talk about that a bit more in a moment. Ignition was in December, and the peak density when an inertial fusion target's compressed is 10 to the 25th particles per cc, which is it's hard to imagine, but yeah, that's what it is. The other main scheme, in fact, the scheme that's received the most funding for energy production from fusion is magnetic fusion done in tokamaks. You may have heard of those. They're basically donut-shaped devices like that one on the upper left. The plasmas confined by magnetic fields. They're basically DC. They're basically steady state as a reactor. That's the intent. And they operate about 1/1,000,000th of atmospheric density in terms of density of the fusion particles in there. But the ones in the middle are hybrid. They're a mix of magnetic and inertial in the sense that they're pulsed, and they use magnetic fields to help confine a plasma, but then the plasma is confined for a while, heated, and then when it burns, it basically burns until it's done with all its fuel. Then you're done, and you have to pulse again, right? So it's pulsed, but it uses magnetic fields, so it's kind of a mix of the two. But this turns out to be these schemes in the middle historically haven't gotten a lot of attention because there wasn't enough funding to do them, really. Okay, there's nothing like the funding that's gone to tokamaks and NIF. Okay, so a lot of the companies have picked them up, and it's just a great thing for the field that these things are being actively explored. Okay, so let's just talk about NIF ignition for a few minutes. So it happened on December 5th, 2022. What happened on that day? They got more energy out, more than 2 million joules of fusion energy out than the laser energy in, which was 2 million joules. Okay. But this wasn't just like, well, let's turn it on. Oh, it worked today. It wasn't that way, right? It's a multi-decade program to do this, which involved systematic examination and variation of a lot of parameters. I'll go through some of the key physics in a minute, but it was a product of numerous campaigns, each of which added to scientific understanding. Really a great example of incremental additions to knowledge that have ultimately got a breakthrough. But anyway, just so that's NIF itself in the upper left there with this little, that's a cutaway, it doesn't actually have a hole in it. Okay. You can see that the target chamber is 10 meters in diameter. The bigger portion of the upper right is the inside of the chamber. You can see the target is that thing up there. The inset is, you can see the beam set up there. Those things sticking in the chamber's 10-meter diameter, those things sticking in are quads. There's 4 beams in each quad. And there's 24 quads in each chamber half. So 4 times 24 is 96 beams on the top half of the chamber, 96 beams in the bottom chamber. And the target is actually held vertically, so the beams come in this way, right? And then the schematic picture, the beams come in. The way it works is they radiate the size of that size of that cylinder, which is Hohlraum, which is German for radiation case. Okay, and the inside is coated with gold or another high-Z material, makes X-rays, and the X-rays compress the capsule. So that's called indirect drive because the laser beams don't compress the capsule, the X-rays do. Okay, yeah, just a little bit more on how it works. So again, just there's on the left is a picture of the capsule. It's actually oriented vertically because the beams come in vertically. So the whole round's vertical. The capsule there in the middle, there's a little pie chart of the capsule itself. It's DT gas and DT solid. That's really intrinsic to the design. It's at the triple point for DT. It's about 20 degrees K. So these are cryogenic targets. They typically take hours to cool and bring to the right condition where you have exactly the solid DT layer and the gaseous region that you want. And also, it turns out the surface roughness of the inside of the cryogenic ice is very important. We'll get into that just a little bit later. But anyway, once you have your Hohlraum in your capsule, the way it works, again, like I said, is the Hohlraum X-ray radiation is produced by the laser interacting with the wall, drives and compresses the capsule. It's compressed down, and then basically it burns as much DT as it can before it disassembles, right? There's no confinement other than just self-confinement or inertia, which is why it's called inertial confinement. Okay, so now I'm going to spend the next few slides getting into a little bit more into the physics because it's a physics colloquium. Okay, and sort of interesting stuff. So this is a picture of the, on the black curve is the laser pulse for the NIF, okay? And the red curve are the shocks that are driven by the laser pulse. So let me explain this. So just first of all, imagine the NIF experiment I showed you, okay? And you might say, well, all right, what kind of pulse would coming out of the laser would give you fusion ignition conditions? Would a square pulse do it? Would a Gaussian do it? The answer to that is no, okay? And the reason why is those pulses have too much energy early in the pulse. They run shocks through the capsule, and it's heated up too much so that it can't compress in the later stages. So we call it the capsule is compressed over that entire 13 nanoseconds, right? And it compresses about 30x in radius. So if you run a big shock through the capsule early on, it heats up and it won't compress because it'll be too hot. So you've got to have a pulse that starts out low and ramps up. Okay, so that's what you need. This particular pulse has got those bumps here. Why does it have those bumps? Well, if you just take a simple ramp pulse, that's great. You can get a nice compressed mass of DT with it, but you have to ignite it. All right. So the way that happens is the ramp pulse provides a nice compressed mass of DT, and then those little bumps on the laser pulse drive in shocks, and those 4 shocks all coalesce at the center of the DT region and ignite a little spark, which then propagates by the absorption of the alpha particles throughout the rest of the fuel. So the important thing is that we use PDB compression here to assemble the mass, but the fuel is not ignited only by DT compression. By PDB compression. That wouldn't work. It's done by timing 4 shocks. So years were spent developing diagnostics to time shocks on NIF. And, it's one of those things that's like, okay, people don't realize the amount of effort it takes to do that. It is a tour de force. Okay. So just a little bit more in physics. I hope this isn't too much, but this is a little cartoon. So it shows the 4 parts of an ICF implosion. This happens to be a picture I got from a direct drive paper, direct drive being a laser striking the capsule directly rather than X-rays, but it's very similar. So the first phase is upper left, early time, then lower left, then lower right, then upper right. So let's just look at it. So early time, upper left. So the laser strikes the target. In this case, it's the capsule, but it could be the whole round also. So when people first started doing inertial fusion in the early 70s, the back of the envelope calculation said you'll get ignition with a kilojoule of laser energy. Of course, now we're at megajoules and counting, right? So what happened? Well, so what happened is, first of all, people did the first experiments. They shined the laser on the target and nothing happened. No neutrons, just nothing, except all the instrumentation started lighting up because they were getting, high energy electrons going through their electronics and all kinds of stuff. So that's what happened. Is there were plasma instabilities that no one understood at the time, which produced hot electrons. So to say it a little bit better, the lasers they used originally were 1 micron wavelength, long wavelength. They interacted with the plasma that streamed off from the capsule, okay, and produced basically some of the light was just scattered, which is not good, but it's just scattered. But there was also a thing that built up due to charge separation of electrons and ions, an electron plasma wave built up. And that plasma wave sucked energy out of the laser beam and transferred it to the electrons. So basically you were winding up with laser energy going to these, hundreds of kilovolt to MeV hot electrons, right? Getting that fixed took 2 decades to do it completely right. And the short answer is you run a shorter wavelength and the laser light is absorbed at a higher density then in a place where it's more collisional. So the electrons fly with other electrons before they have any chance to pick up more energy. So that's
Chris,
yeah.
NIF, I thought they were 1064 and they frequency double.
Okay. They double and then they run a quarter micron. Sorry, 1/3 micron. So they double, and then they do, what is it? They do nonlinear frequency mix and they get 1/3 micron.
Okay.
Yeah. So I'm sorry. I think my slide said 1/4 micron, 1/3 micron. I was thinking of one of the startups. Yes. Anyway, it's not nonlinear frequency. Right.
How much of the momentum transfer is from ablation to the outer layer?
Oh, that's a good question. Well, I'm not sure. I have to think about that. I can't give you an answer right off the top of my head. Yeah. How much of the momentum transfers? So the absorbed energy, the total absorbed energy in the capsule actually isn't that great, actually. So it's probably a pretty small fraction of the incident laser energy. Because I mean, there's probably only what 15 or 20 kilojoules in the capsule. Yeah, Jim?
I was gonna say, I mean, in terms of momentum conservation, it is just, you know, the ablative mass that's driving momentum into the capsule. And the efficiency that you can couple the laser to that process is related to the laser plasma. So.
Yeah, so back to that, yeah. So, and that the coupling is a complex thing, yeah. And then in the next phase, in acceleration, you start to get into the hydrodynamic instability phase, right? Because you've got the ablated plasma pushing on the capsule, right? So you've got light pushing on heavy, light material pushing on heavy, so that interface is unstable there. And so, you know, there's been a lot of studies about, which one of the modes are most dangerous for this, right? Because you have to look, there's all kinds of different modes, right? And it's generally around, it's actually, the very low mode numbers are smoothed by geometry. For the implosion, it's around L equals 20 to 40 are the modes that are bad for hydro instability. And then later on in time, as the capsules continues to be compressed, and then and the DT gas becomes more compressed. So the DT gas starts to push back. So the inside of the ice surface becomes another unstable point, actually. So you've got to worry about instability growth there. And finally, you've got to worry about the hydro instability growth breaking up the shell and causing the shell to get into the fuel and cool it. So hydro instability is a huge thing there. And then, of course, there's all the physics of propagating burn, which it looks like based on NIF experiments, we understand pretty well. So that's just a quick tour of some of the physics. And so the way this all lines up is these are the experiments done over time. So NIF came online in 2009, and so these are fusion yields versus time. So you can see the yields the different colors or different campaigns, chiefly varying things like the symmetry, the capsule size, the whole realm size, and all based on data and modeling and simulation. The steady increase eventually resulted in NIF in ignition in 2022. There's a great art review. There's in fact another one just came out today. There's a great review article by Omar Hurricane that goes through these ignition campaigns and talks about how it was actually done. But we've demonstrated that. So I mean. I'll talk about tokamaks in a second, as we'll see, this is great, but for a reactor, you actually need to get gains more like 100. So we have a ways to go here. Okay, and we'll come back to that. Okay, so real quick comparing how machines stand. So I talked about tokamaks earlier. These are some of the big ones that are underway being built. So JET in the upper left just was a workhorse for the World Fusion Order program. It just closed. ITER on the lower left there is under construction. Probably heard about it. It's over $40 billion. It's the most complicated device ever made by man. And so it's really something. I'll show you another picture of it in a minute. That will get 500 megawatts of fusion power by when it's done, which we'll see when. There's a private company called Cambridge Fusion Systems building a small tokamak there with high magnetic field, right? So basically it can maintain higher density than a normal tokamak. And so it can be a lot smaller. You have superconducting coils versus non-superconducting coils on jets, and ITER will be superconducting. So in any event, very excited because the Cambridge Fusion System looks like it will work. It's actually the very logical thing to come out of the US program if the US was still building new machines. This is a picture of ITER. Just gives you a sense of scale. The thing is truly immense. That's one toroidal field coil. So imagine, this is an older picture. Imagine the entire room was filled in with those big coils, and that's the ITER tokamak. And its goal is 500 megawatts, sort of power station scale production for a couple of minutes. So where do we stand on these things? So there's this thing called Q, the scientific Q, which is driver energy in divided by fusion energy out. Okay, and the driver energy in for NIF again over. So for NIF we've achieved 2 or 3 to 1 right now in that 2 megajoules in, and right now up to 5 megajoules out. It's not all published yet. Okay, NIF is the only machine that has gotten Q scientific greater than 1. The tokamaks are close. The jet machine that in the UK got 0.64, which is great. So magnetic fusion has made very steady progress over the years and is almost at that ignition threshold. Okay, ITER will vastly exceed it. And we think that Spark machine, which is being built by a private company and will start running in 2028, actually should achieve the same conditions as ITER. So this plot's a little messy, but it summarizes it. So there's this quantity called N tau Ti, density times temperature times ion temperature, which is sort of a common unit of fusion, and that's on the left. Don't try and figure that all out, but and in the plot you can see red is tokamaks, black is lasers, and green is stellarators, and different schemes. It's plotted by schemes. And you can see the equivalent Q is lined up above. So you can see that, NIF has exceeded Q equals 1. TFTR, which is a machine that was running in the 80s at Princeton, and JET are just under Q equals 1. Spark, the private sector machine, and ITER should both exceed Q greater. But the Spark will do it a lot sooner if all goes well. So that's where we're looking in the short term. Just winding up here, just looking a little bit more at if I wanted to make fusion energy out of NIF ignition, how would I do it? Well, so NIF shoots a couple of times a day. Okay, so if I want to make a power plant, I got to shoot 10 times per second. Okay. Well, it turns out we have ideas on how to make lasers that run at 10 hertz. They use diode pumping. The cost of that right now is very expensive at the volume we need to do it, but in principle, it works, right? But now you need 10 targets per second. Okay, that's a little harder, right? Remember, I told you it takes hours right now to fill a NIF ignition target with DT and to get the layer and everything exactly right for ignition. Doing that at 10 hertz is going to be a challenge. So it'll probably be something different. The program right now is exploring things like wetted foams. Okay, so you would have a foam matrix which would hold the DT. So that's a different target design rather than a gas solid. Okay, but that's the research program right now. Of course, and then you also have the blanket I told you about, which can this is the example is a lithium blanket. It's fluorine lithium. Okay, so basically the lithium's there to breed tritium from the neutron. You also capture thermal energy from the neutron, which drives the electrical production. Right. And so that's it schematically. But in order to make this work, you've got to get, we need much more gain than NIF has. Right now, NIF has gains of a couple. We need gains of 100. We need fuel drivers and targets. But the good news is the Energy Department, after many years, the Energy Department did not support technology development for inertial fusion at all. Right. They only supported magnetic fusion because inertial fusion was for national security purposes and physics. So, but now they're supporting it for energy, so that's good. And so we're going to make progress on some of these challenges. So just a little bit on commercialization. So there is it's very active around the world because of these results and the excitement, right? So private equity is putting significant money, over $7 billion a year now, over 40 companies around the world. In the US, it looks like this. Up here in the Northwest, we have, ZAP, Helion, and Avalanche, as well as Exofusion, which actually looks at diverters for tokamaks, and then Kyoto Fusion Engineering, which is a general engineering services company. But there's a lot of activity in the Bay Area and in Southern California. In Boston, you can see Cambridge Fusion Systems. They're building the Spark tokamak I mentioned. It turns out that's 5 minutes from where my mother lives. So next time I go see my mother, I'll get a tour. I hope. Very exciting there. Okay. Now, one of the things that DOE has said is that they want to pursue public-private partnerships for fusion. So one thing that WSU is doing, one of the things I'm doing, is putting together ideas on how to do public-private partnerships for fusion. So DOE was kind enough to give us a $150K grant, support a workshop on this subject. So at the end of next month, all these folks are going to be there, 10 companies, which I don't think 10 fusion companies have ever been in one place talking, but it would be interesting how much they want to talk to each other. We'll see about that. But, 5 universities, 2 labs, and our local economic development, Clean Tech Alliance and the Tri-Cities Economic Development Group, TriDec, and then DOE and Washington Commerce is going to come. So, we'll see if we can figure out a way to really launch private public partnerships for fusion energy, which is what DOE has basically said, I don't have the money to help the company do this. So it's just you all are going to have to work together to make this. But so you could easily imagine that, the companies have certain things in common, like how are they going to deal with neutron activation, neutron damage of their reactors, right? They all have this problem. They all need a blanket, right? There's so many things that they have in common. The things that they don't want to talk about are their secret sauce about how to get more fusion energy out and energy when to heat it. So anyway, with that lightning tour, I'll just close here. So just 2 messages. So first of all, HED science, really an exciting field. I urge you to read that National Academy. It's kind of thick, but you want to see more. But just fascinating stuff in astrophysics and other areas. You can come and see me or Brian or Dan or Jim. People will talk more about it. So it's really an exciting time for that field. And then of course with fusion, with private sector investment now dwarfing what the government spends, who knows what's going to happen, but should be very interesting. And again, I've just emphasized that the achievement of Q scientific greater than 1 on NIF is truly a Wright brothers achievement, right? And that means the self-heating by the alpha particles works. We've now demonstrated that. Okay, so the next 20 years or so will be very interesting. So thanks for your attention.
Plutarch, time for question.
Yeah, so the technology that ITER and like employs is very different from NIF, as we explained.
Yeah, yes.
But how different are the timescales?
Yeah.
Will ITER become obsolete, for example?
Well, yeah, I mean, if Spark achieves the same goals as ITER by 2029, yeah, that's going to be a problem. If you're ITER. But that we'll see. I mean, the sort of the lessons of fusion have been that it doesn't ever happen like you predict. So it maybe Spark takes longer, and then ITER has got a ton of technology in it that's very useful for reactors. It's designed explicitly to test a lot of reactor concepts. It's got a blanket module, things like that. So I don't know what'll happen. The EU, the other thing with ITER, with world great power competition could be trouble for ITER because Russia, the US, and the EU were partners in ITER, and that's still holding together, but don't know if that'll hold together as is China. But the timescales, I mean, ITER is another essentially DC machine in principle.
I have a question about the illumination for the NIF facility. So we have that cylinder. You said it's plated with gold.
Yeah.
It's a special material, which you said was you said it was a certain name. I forgot the name.
It's a whole I mean, it just means radiation case.
Okay, so the light comes in and it illuminates the edges of the cylinder.
Right.
Oh, why is it beneficial to do it there and not pre-prepare that light and then shoot that light at the target directly?
Oh, yeah. I mean, why is it better to a great question. And the answer is that both schemes have been pursued extensively. The light on the target directly is called direct drive. The light this way is called indirect drive, right? For obvious reasons. So the short answer is the advantage of this are a couple of fold. Number one, the whole round provides what we call geometric smoothing of the radiation field that strikes the target, right? So with direct drive, you've got to make the beam strike the target. If 1% RMS uniformity to compress at 30x in radius, 30 to 40x. So symmetry is easier here. It also turns out the way the X-ray physics works, that X-ray driven implosions are more hydrodynamically stable than laser-driven implosions because it's X-rays, the energy is absorbed deeper in the capsule, you get a longer scale length for the density, and so it turns out to be less unstable. Okay. On the other hand, direct drive is of course more energy efficient, right? I mean, you're not taking that step of converting the laser to X-rays, right? And there's a few other advantages of direct drive. So direct drive is really avidly pursued. And to just make it more confusing, we actually do direct drive on the NIF. We figure out a way to do it. Not as well as if I arrayed the laser beams uniformly around the chamber, but we can study direct drive. So it's an active area.
So maybe a follow-up question, is the cylinder seemingly the best kind of geometry for the whole world, or are there other geometries?
Oh, that's a great question. There are other geometries.
Would the spherical one be studied?
Japan uses spherical holograms. Actually, yeah. So yeah, the answer is yes, and there's other ways to do it. For NIF, this is so well characterized that we had a path to ignition. We just stuck with it. But there's lots of other candidates.
So the celebrated event here from December 5.
Yeah.
Was this like a one-time event or is this repeatable?
Oh, yeah. No, it's been, I don't see, the problem is they don't publish, they don't publish it all. Not yet anyway. So short answer is, okay, so that there have been 4 or 5 ignition shots since this one. And the max right now is 5 megajoules.
Okay, so it wasn't just a unlucky shot, but it's.
No, it's been reproduced. Yeah.
Right.
So does NIF make tritium on site? Like they keep lithium-6 nearby and wait for neutrons?
No, we typically get it from another, it's actually this funny thing, I get it from Canada. It's a long story. You get it from Ontario Hydro.
Okay.
It's simpler. So that's what we do, but we make no tritium.
Okay.
I mean, there's places that make tritium that we could get it from, as part of the weapons program makes tritium, but we don't get it.
So the 100 times gain that we need, does that account for the wall efficiency? Because lasers are not terribly efficient converters of electrical power to photons. So do we need 1,000 times gain to go over the wall, because this is scientific yield.
Yeah, right. Yeah, I think that's right, Dan. The actual gain you need is going to be a little bit somewhat higher when you factor in all the conversions you've got to do. I mean, that's generically you need numbers in the hundreds. Right? I mean, the exact scheme, maybe a little bit, but you need a lot more than we have here.
So this conference that you advertised, when is it actually going to take place and where?
It's going to take place October 23rd, and it's going to be at WSU Everett, actually.
Oh, I see.
Where we have Seattle Fusion Week. So I should say there's a thing called Seattle Fusion Week. And it's October 21st and 2nd and 23rd as well. And it's in Seattle on Monday and Everett on Tuesday and Wednesday. So the nice thing about it is if you're interested, and you sign up in advance, they offer, some of the companies will sponsor tours. But because they're fairly secretive and they're busy, they don't decide until the last second. So what you have to do is register and then hope that they have a tour. I'm sorry about that, but they probably will.
I noticed that Cambridge isn't on the list.
Oh, it's on the, well, it's Spark.
Oh. No, on the conference side that you're putting together, you had the list.
Oh, well, we couldn't get it. We couldn't get everyone. We started out with the companies out here.
I see, okay.
Yeah, so the title of the workshop is actually Western US Regional Hub. So
I see.
we did UC, UC, Colorado State, and University of Nevada, Reno. But there's more. We can't do it.
Good. Maybe one last question, but
So within roughly your last 5 or 10 slides, you had this graph over the decades of progress.
Yeah,
And you had a density measure up.
I think, this one?
There.
Okay.
So is this related to the Lawson criteria?
Yes, that is essentially another version of the Lawson criteria and tau TI. So, I mean, and it's a little better because it commutes better between magnetic and inertial. So, and so the classic Lawson criteria is n tau, confinement time times density. Throwing in the ion temperature allows a simpler comparison, but that's basically what it is. That's a constraint on n tau.
It's amazing how long it's taken to make the progress, because people in the 1950s were trying to come up with ideas to get closer. But anyway, thank you. I just.
Well, yeah, so there's a great talk on history of ICF that a colleague of mine, Mike Campbell, gives, and he talks about that. I mean, I get one part of it, certainly it's harder than we thought. Like when John Knuckles, so you probably heard, John Knuckles is the one that came up with laser fusion, and he said it's 1 kilojoule will do it, no problem. That didn't work. And the magnetic fusion had the same issues, right? I mean, there are a whole host of plasma instabilities that tokamaks have to deal with, disruptions that people had no idea. Thank you.
Right, maybe the best, let's thank Chris again for questioning.
Oh, yeah.
So what I do is I work with
your
and that's kind of where that thought came from. I was thinking, well, let's just give more meanings.
Yeah, that's interesting. Yeah, right.
And I was just thinking, well, if you just get enough laser power, these stuff irradiate and cesium.
Yeah.
Could you theoretically hit fusion?
I don't, probably not, because you don't just need power, you need, you need n tau. You need density. Yeah, right. Yeah, you need, you need to concentrate.
Because in our cloud, it's all
Yeah, because, fundamentally, you have to.
Hey, Chris, can you hear me?
Is
Audio in the room?
Are you aware of producing?
Testing,
Yeah,
testing.
And then heat the rest of the plasma. So if it's low density,